So here we are looking at algebraic properties of finite sums that are going to be particularly useful when we start looking for the general formula for a Riemann sum and that limiting process. So here we go. To begin, we want to let a sub k and b sub k be finite sums of the kth term. So these are those general formulas of each sigma. So arbitrary general formulas. We also want to go ahead and let c be any constant, any real number your little heart desires. So the first rule is the sum and difference rule. So if you have the sum from k is 1 to n of a sub k plus or minus b sub k, we can separate this to the sum or difference of the two sigmas. So this is equal to the sum from k is 1 to n of a sub k plus or minus the sum from k is 1 to n of b sub k. Our second rule is called the constant multiple rule. So here, if we have the sum from k is 1 to n of a constant c multiplied by this general formula a sub k, then we can pull that constant to the outside of the sigma. So now I have c multiplied by the sum from k is 1 to n of our general formula a sub k. Our third rule here is the constant value rule. So here, if we have the sum from k is 1 to n of just a constant c, then this is equal to that constant c multiplied by n, and this is such that or where n is some integer value. Our fourth rule is the sum of the first n integers. So let's actually think about this expansion first. So if it's the sum of the first n integers, we're thinking about 1 plus 2 plus 3 plus all the way up to n. And so we can write this in its compact sigma notation form as the sum from k is 1 to n of k. Now this simplifies to the general formula n multiplied by n plus 1 all divided by 2. And so these next three rules are going to be particularly important for finding the general formula of Riemann's sum. And we can prove this formula using induction, which we see in discrete structures. Our fifth rule is the sum of the first n squares. So again, let's think about this expansion first. This would be 1 plus 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, which is 16, and we can keep going until we get to the nth term squared. So in this compact form, this is the sum from k is 1 to n of k squared, and this reduces to the general formula n multiplied by n plus 1 times 2n plus 1 all divided by 6. And again, we can use a proof by induction to easily show that this is holding true. But here in this class, it's going to be particularly useful for reducing our algebraic sums for finding Riemann's formula. And last but not least, we have the sum of the first n cubes. So again, thinking about the expansion, this is 1 plus 2 cubed, which is 8, plus 3 cubed, which is 27, plus 4 cubed, which is 64, and we can keep going until we get up to n cubed. So if we put this in our cute compact form here, we have the sum from k is 1 to n of k cubed, and this reduces down to the formula n times n plus 1 all divided by 2, and this is squared.